Hey, hello everyone. Welcome to the presentation. And my name is Jingyao Gai. I was graduated from Dr. Liu Tang's lab last year, and currently I'm working as an assistant professor in Guangxi University from China. Today I would like to share my experience in developing a control system for a robot using ROS framework. Hope this could help everyone to have a perception of the tools we are using and the roadmap we follow to develop a robot. So there are many robots in different types developed for different applications, like ground robots in transportation, like autonomous driving, and legged robots as service robots. These are ground robots. Also, there are also robots in the water and in the sky. So what do they have in common? I would say they have the same kernel, which is called ROS, Robotic Operating System. Developing a robot was time-consuming, very time-consuming. We took time to write the code and more time on debugging. But for most of the time, we were reinventing wheels. So that's why we use ROS. This picture is from the official website. I think it explained the original intention of ROS pretty well. So ROS was designed to be a framework that can support all kinds of robots, like both drones and autonomous driving. Also, it provides reusable tools and foundations for developers to use directly. So we don't need to spend too much time on reinventing the wheels. So what is ROS? What is Robotic Operating System? I would say it is a middleware, or it's a framework to build a robot. So under ROS framework, the robot is acting as a company. So imagine company, there are multiple nodes like workers with different skills and working on different tasks. So in order to run the company, these workers need to communicate, share the information, or pass material from nodes to another nodes. And in ROS, under this ROS framework, there is a master, ROS master. It acts as a router or the server. It formed a local network, and with this network, each node can send the information and pass material to the other nodes. So for a complicated robot like this, it needs a lot of nodes. For example, sensor nodes and motion control and some planning, arm planning nodes. Actually, we can find most of the nodes from publicly available packages, and we can directly plug and play. So what we need to do is just act as a manager and organize these nodes instead of doing everything by ourselves. Another highlight of ROS is the simulation. Simulation is crucial for developers. Once we develop a program, we need to test it whether it is functioning or not. So if we directly try it on real robot, there is a risk it can go crazy and break itself. So we try it in simulation first, and it takes less time too. Sometimes the code works just fine for one scenario, like this call. But we need to test it in different scenarios to make it more stable and robust. In Gazebo, Gazebo is the most popular tool, and we can try different scenarios before porting the code into the real robot. And there are some other features of ROS, like it supports C++ and Python as the languages and operating systems. For ROS 1, it only supports Linux, and for ROS 2, it supports more. There are a huge amount of existing ROS libraries available and ready to use. For example, those are motor controllers, sensor drivers, like motion planning, and even robot arm control. Another thing to mention is the ROS community. So right now, ROS is actively developed and maintained by a global committee called Open Robotics. It's huge, active, and growing. And the most important activity is called ROSCon. It's like a conference where the developers share their current progress and share new key features for future version of ROS. And there are many three useful websites. ROS Wiki, which is like a Wikipedia in ROS, and ROS Answers is you can ask all kinds of technical-oriented questions, and there are many answers. The community will answer those questions for you. And GitHub, people share their code on it, and we can also make contributions. So ROS is pretty cool. Is it hard to use? I would say yes and no. As a quick start to use ROS, first we prepare a computer running Ubuntu. We need some Python and C++ language, and a cup of coffee, some music, etc. Then we install ROS on that computer and start the tutorials. There are a bunch of tutorials in this Wiki ROS website, and some of them I would say very fundamental and unnecessary, like we need to configure the ROS environment, the file systems, also the ROS packages and the ROS nodes, and understand how do they communicate with each other, as well as some useful packages like TF, URDF, control navigation. After that, I would say congratulations, you can program a robot now. Well, is that true? Yeah, but no, still. Control system development is never an easy task. Because of robots, the software is too coupled with the hardware, and there must be a lot of issues during the development. So in addition, some modules you want might not be available. At this time, you need to dig into it. And there are some useful resources for learning ROS. The official wiki is always the first place to search. And there are some YouTube channels provides very high quality ROS tutorials. And also workshops. A lot of books are available. I really like this last one, the integrated ROS learning platform. That one has a bunch of tutorials as well, and you don't need to install the ROS on your computer. That website provides that platform, and you can directly put your code on it. It's really good. So developing a system is really a big project, and now we have the tool already, which is ROS. The next would be how to use it. And where should we start? Here is the roadmap I use for developing the control system. First, we need to have the robot designed. And during the designing, we need to identify what kind of problem and to solve and what's the objectives. And then select the proper actuators and sensors for accomplishing this objective. Then we model this robot and analyze what's the scale of the system, what's the kinematic and dynamic of the system, what kind of environment we're in, and then separate the robot into a series of bodies, joints, like actuators, sensors. Then derive a series of equations for motion control, like what's the velocity versus the wheel RPM. After modeling, we design this control system architecture, and we have the architecture. We implement each module in the architecture and perform tests in simulation. This could loop a lot of times and until we are satisfied. So model, design, and implement, and do this again. After we are satisfied, we port the real robot to port the code to the real robot prototype and test it on the real robot. We have a case study here, so use our PhenoBot 3.0 as an example. So PhenoBot 3.0, as Dr. Tang has introduced, is a high-throughput in-field phenotyping robot. The robot was designed for organ-level phenotyping, and it should have the it should do autonomous driving as well in this narrow crop roads. So based on these objectives, we designed the robot to have a narrow and articulated body and differential gears, auto-balancing sensor mass, and a bunch of sensors mounted on the sensor mass for phenotyping, and also a bunch of sensors like GPS, MU, and cameras for navigation. The first task is the robot's modeling. So based on the scale, we disassemble the robot into minimum number of parts, including the sensors. For example, the robot has a front part and a rear part and connected by a steering joint. So in the bodies, we separate that into like a front part and the rear part, revolute joint connecting them. Front wheels connected to the front part through a continuous joint, also for the rear part. And on the center tube connected to the rear part, we have a revolute joint controlling the mast balancing, which balance that mast. And the mast has a prismatic joint for like mast telescoping. By defining those bodies, we can create a model inside this simulation environment. As well, in addition, we also modeled the crop plants in rows, and also we want to test whether the robot will function in, with uneven ground. So we also created this uneven ground. This is in Gazebo. So next would be the kinematic, the modeling for motion control. Since our robot doesn't drive very fast, we only consider the kinematic model of the robot. The body is quite special, so we developed our own model. It's a simplified 2D bicycle model, and we, based on that model, we derived what's the relationship between linear and the angular velocity with the wheel speed and the steering joint position. This would help us to figure out like for a desired robot movement, desired linear and angular speed, what would be the wheel speed? How do we control the wheel speed? And how do we control the steering joint position? After modeling, we can design the architecture of the navigation system. The navigation control system should have the following modules, which is similar to autonomous driving. It should have like a sensor drivers, very low level, and motion controller, which is based on the linear and the angular speed command. We send the proper commands for the motors to move. And the robot localization, the robot needs to know where it is before navigation, and then navigation, including path tracking or like planning paths to a goal. Then vision-based positioning, we can do some like a visual guidance, and also we can also map the field, like where are the crop plants in the map. So as we mentioned before, we should act as a manager for this system. But how do we organize these modules we just mentioned? And how should they communicate with each other? So this is the architecture diagram showing the answers, showing my answers. So as the data flow, data should come from different sensors and then fused for localized robot. Then with a field map, a path was planned and then tracked to accomplish a certain task, such as traversing the crop rows. And during tracking, the computer computes how to drive the robot to reduce the tracking error, then calculates the command for individual motors based on the kinematic model of the robot, and then send the commands to the motion controllers, which is another hardware. So we already have the big picture. Now we draw the details. The motion control module, it calculates the wheel speed and the steering joint position to control the linear velocity and the angular velocity of the robot based on our derived equations, right? So how do we start? We can start with this package, which is a ROS controller, Kalman steering controller, because this package uses a similar strategy. It's good to start with this package. The next module is robot localization. This tells the current position, heading, and the velocity of the robot. So fusing GPS, MU, odometry is a common strategy. So since we use a Kalman filter, we can directly use robot navigation package for this. After implementing control and the localization, we could start a test in simulation to verify the performance for motion control. So first we turn on this Gazebo simulation environment, and we can see the robot is here, and also the uneven ground, the crop rows. Another tool we are going to use is this RQT here. And RQT is a powerful tool mainly for diagnostic. For this robot steering tool, it can directly send a speed command to this robot. For example, right now I'm sending a 1 meter per second forward command to the robot. You can see the robot moves as we expected. And then we want it to go back. Go back. Okay, it's going back, and we set 0.5 meters per second forward and apply angular speed. So it should turn around 10 seconds for half a cycle. So okay, it's moving as we expected. So the motion planning works fine. In order to test the localization, we need to turn on RVs. So RVs is a tool for 3D visualization of the status of the robot. And this one, when we are running the actual robot or the real robot, we still use this tool for visualization. But when using the real robot, we are no longer using Gazebo. So we can see currently it figures out the position of the robot, and let's move it. So it's adjusting its position. That's due to the Kalman filter. And we let it go back and turn. You can see it's still, the position is correct and the heading is correct, so the localization works fine. After testing the robot motion control and the localization, let's move on to the next module, which is robot navigation. Robot navigation relies on the robot motion control and the localization. So navigation has two modes. One is goal reaching, which is we define a goal first, and then the robot can plan a path, which is a collision-free path to reach the goal. this is usually for navigation indoor and used with a LiDAR. And for path tracking, usually we define a path and let the robot follow that path. This is more often used in agriculture, since the crop rows are pretty known, and we can just plan a path for the vehicle to follow. To start with, we can use this navigation ROS package. For path tracking, the main objective is to reduce the tracking error. So the tracking error has both heading error and the position error. So many methods are available. For us, we implemented three methods on our robot. The first algorithm is LQR, which is a feedback control method. It controls the robot steering based on the current and the previous tracking error. The second algorithm we use is called pure pursuit. It's different from the first one since the principle is like this. The robot looks a certain distance ahead and then calculates an arc path to correct the tracking error. So it's looking ahead, not the past. The third algorithm is called a timed elastic band. It's a variety of model predictive control. We can learn the name is predicting ahead. So it plans the motion several steps ahead and select the best plan to minimize the tracking error and reduce the chance of collision. So for feedback control methods such as the PID and the LQR we said before, they're just looking past, right? So another good thing about this one is during headland turning, since for the robots, they need to change the roads, right? The algorithm can generate like this fishtail shaped path that takes a minimum space. So after developing these navigation modules, we come to simulation and test it. So first we use this diagnostic tool like RQT in ROS to verify that the nodes we built they are connected correctly as we expected. After checking this, we can run this simulation in Gazebo. So this simulation use pure pursuit control and follow a predefined path. So this is the simulation and this is RVs. RVs is for monitoring the robot movement. When we are using the real robot, we also use RVs, but we don't use Gazebo. Gazebo is only for simulation. You can see it entered the roads correctly, so our navigation system works well. This video shows our previous results using the timed elastic band algorithm for dynamic path planning during headland turning. So we can see that it's doing a fishtail turn, right? And enter the crop rows safely. So since we have tested our robot in simulation and everything works fine, we port the code directly to the prototype in the real world and perform field tests for evaluation. So this is test conducted in 2018. And since it was late season, the corn plants, they are all yellow. Yeah, it's also following a predefined path and then entered the crop row safely. And we also recorded the trajectory of this pure pursuit control algorithm, and then we can analyze the tracking error and come to like a statistical performance parameters. Well, the previous test used GPS for localization. Although it works fine in that field test, but in sometimes when the crop plants they are pretty tall, they may block the GPS signal like this. So GPS signal is not that reliable. Therefore, we want to have an additional clue for navigation, and the computer vision is pretty a good choice. The most widely used strategy for vision-based navigation is crop row detection. So there are many sensor setups. For example, above canopy cameras, which is suitable for short plants. And for tall growing plants, we usually use under canopy cameras sensors such as LiDAR, and we use the time of flight camera. So this is an algorithm implemented on our robot, which is using an under canopy time of flight camera. So time of flight camera, it outputs a bunch of 3D points representing the position, the shapes of the objects in the view. So in these points, we could find the crop rows by fitting like 2 walls, and then we can determine like where the robot is relative to the crop plants. And the library we're using is called the point cloud library. It's in C++, processing this point cloud data. In addition, we implemented another algorithm which is using a top monocular color camera for robot navigation when the crop plants they are short. This algorithm uses 2D Fourier transform. Well, that's since the crop rows they are just like a sequence of waves. They have the same spacing, right? So that fits the concept of Fourier transform pretty well. So that algorithm was designed or implemented using this OpenCV library, which is a library mainly designed for computer vision applications. So we tested those algorithms directly on the real robot, since the simulation cannot simulate those crop plants pretty well. So in this field test, we can see the robots can detect those crop plants precisely, and the robot just controls itself to stay in the center of the crop rows. So thank you for listening. I apologize that I cannot answer your questions directly, but you can always reach me using my email, or you can directly contact my advisor, Dr. Tang, and he can forward the question to me. Well, thank you again for your listening.